And the first speaker is Elia Bruè from Università Bocconi di Milano, and he's going to talk about non-uniqueness and flexibility in two-dimensional Euler equations.
Thank you very much, Camillo, for the introduction and for inviting me. I'm very happy to be back in Princeton after a year and a half. I was supposed to here from 2020 to 2023. And I'm very happy to talk about this work, which is some follow-up of what I did here as a postdoc. So let's start. So this is about two-dimensional Euler, uniqueness, flexibility questions. So let's start. So this is the model I want to consider, just two-dimensional Euler equations. Here U is my velocity field, and the domain is the two torus, so I'm assuming periodic boundary conditions, just for simplicity. P here denotes the scalar pressure, and I'm imposing incompressibility, and the first equation is just the momentum equation. I'll be interested mainly in uniqueness and well-posedness questions. So I consider the Cauchy problem associated with these equations, and U0 just denotes the velocity field at time 0. It's my initial condition. Okay. In two dimensions, it's very convenient to rewrite the Euler equations in terms of the vorticity. The vorticity is a scalar, is defined as the curl of the velocity field, is given by this equation here, and in two dimensions, it's just a scalar function. And it turns out that the two-dimensional Euler equations can be rewritten as an active scalar equation. So they have a structure of a transport equation where omega is the vorticity, U is the velocity field, and this relation, which is called Biot-Savart law, is nothing but the connection, the relation relating the vector field and the vorticity. This is a very nice operator of order -1, which inverts the curl operator. Now let's just make a few very basic observations. Given the transport structure of the equation, it's kind of natural to expect that the LP integrability of the vorticity propagates in time. And in particular, one expects that for every p between 1 and infinity, the LP norm of the vorticity, of the initial vorticity, the vorticity at time 0, should be constant. So in particular, if we have a uniformly controlled vorticity, we can try to look at the velocity field and try to understand what kind of a priori bounds we get. And it's easy to check that the differential of the vector field is more or less of the same magnitude of the vorticity itself, since there's here an operator of order 0 relating the two, which is Calderon-Zygmund-like. So in particular, when P is any exponent between 1 and infinity, we expect to get some LP bound on the differential of the velocity field uniform with respect to time. While when P is equal to plus infinity, we cannot get an L infinity bound, ellipsis bound on the vector field, but almost. One can get a BMO bound. And this is telling us that very likely the equation is going to be well posed when P is equal to infinity, since we have a transport-like equation. I mean, it's not a linear equation, but it has the structure of a transport equation with a velocity field which is almost Lipschitz, and so it can be treated with some variant of the standard Cauchy-Lipschitz theory. And even when P is smaller than infinity, we have a good uniform bound, a good Sobolev bound on the vector field, and in the linear setting is well known by the Di Perna Lyon's theory that transport equations with integrable densities and Sobolev regular velocity fields are well posed, at least in certain range of exponents. So it looks like some rigidity in the class. I mean, when we consider initial vorticities in LP, seems to be appearing in this problem. And when p is equal to infinity, a well-known result dating back to Yudovich in 1963 says that the problem is well posed. So here I'm presenting a statement over the two-dimensional torus. The original theorem was in the Euclidean space of dimension 2, but I mean the statement is the same. And it simply says that if we consider vorticity, a velocity field at m0 with bounded vorticity, then we can construct a unique solution in the class L infinity space and time, with of course the correct initial conditions. So the problem is well posed, and we have a flow in the class of L infinity, a well-defined flow in the class of L infinity vorticities. And it is possible to prove that when p is an exponent between 1 and infinity, there are solutions given any vorticity in LP. One can construct a solution to the Euler equation with vorticity in LP space and infinity time. So there's existence holds even when the vorticity is not bounded, but just integrable. And then the natural question is about well-posedness and uniqueness. So we have solutions for every exponent p. We have a uniqueness result when p is equal to infinity. What can we say about the case p between 1 and infinity? And this is a very old and fundamental question in the field. And today I would like to present a few developments, mainly in the negative direction, regarding this question. And then I'll focus on flexibility and convex integration solutions in this class when p is a small exponent bigger than 1 but small, and which is the main new result I got in collaboration with Maria Colombo and Anush Kumar. And the first result I want to mention is a theorem by Vichik in 2018, and it's, in my opinion, maybe the strongest evidence of non-uniqueness in this problem. And it says the following: if we add an extra degree of freedom, an external body force F, and in this specific theorem, the body force is integrable, is L1 LP in space and L1 with respect to time, and actually is much better than this, is smooth for every time t positive, and the only singularity is at the origin t equals 0. At the space origin at time t equals 0. And here is the problem, is just two-dimensional Euler in the two-dimensional space, in the Euclidean two-dimensional space instead of the torus, with this external body force, which is given. I mean, there exists one such that if we impose as initial vorticity 0, then we can construct at least two distinct solutions with the same initial condition 0, the same body force F, and belonging to the natural classes. So the vorticities are L1 and LP. P here is fixed, there is an exponent between 2 and infinity, and the velocity fields are bounded, and they belong also to the energy. I mean, they have finite kinetic energy, L2 in space, L infinity with respect to time. So actually, this statement is a small variant of the original theorem of Vichik, and when I was a postdoc student here in 2021, we started this reading seminar with Camillo and other 8 students here at the IIS, and we reviewed this result and we wrote down this lecture notes. So you can find this statement and a proof of this result in this lecture notes. Now, let me just say something about the key features of this no unique solution. So here the key word is symmetry breaking. So what happens is that the external body force F is just a radial object. It depends on time, it has a similar structure, and is radial. And the first solution, the one I denoted omega-1, is again radial, is rotational invariant. And this is exactly what you expect, given the symmetries of the Euler equation. If we consider an initial condition, which is radial, I mean, it's trivial, in particular, it's radial, and an external body force, a radial external body force, we expect to find radial solutions. And indeed, the first solution is radial, but the second one is not. The second one depends in a non-trivial way to, on the angular variable in R2. And so the idea is that the responsible here for this symmetry breaking is the external body force. The external body force, I mean, here there's some very strong form of instability hidden in this problem. And this instability is the main responsible for the existence of the second solution depending on the angular variable. And one can rewrite the system in self-similar coordinates. In this coordinate, the system does not depend on time. And the first solution, omega-1, should be understood as a radial steady state of the problem, while the second solution is just one trajectory in the unstable manifold, constructed starting from unstable modes of the linearized problem. So the unstable object is the profile, and the second solution is just one of the unstable trajectories coming out of this unstable manifold. And the presence of the body force here is extremely important, as in order to show instability for a certain profile, in order to get rid of the body force, one should find an unstable self-similar solution of the Euler equation, but this seems to be a very, very difficult problem. And the one constructed by Wyschik here is a stationary solution of the Euler equation in standard variables, but is no longer a stationary solution in self-similar variables. It's just a vortex. Okay. There are, after this work, many refinements and simplifications have been obtained by different authors. Here I'm mentioning the work by Castro, Faraga, Mengual, and Solero. They found a very nice construction of the unstable vortex based on finite dimensional reduction. And I want to also mention the work by Dolce and Mescolini. They simplified the nonlinear, the construction of the nonlinear manifold by employing this very nice trick due to Golovkin's. And I also want to mention actual result in the opposite direction. It is possible to show that this specific singular vortex is stable. And this is well connected with this result, as in order to get the very same symmetry breaking with a radial singular initial condition and zero body force, the only reasonable candidate as initial condition is this vortex. But it turns out that this is stable, so no way one can eliminate the body force, keep the symmetry, and conclude the proof of no uniqueness by means of this kind of ideas based on instability in self-similar variables. And finally, let me mention another result we got again when I was a postdoc here at the IIS with Dallas and Maria, and we used this ideas to construct the first example of no uniqueness for the resolutions to the Navier-Stokes equation with external body forces. So here there's a type I should add plus F. So we have a body force for the very same reasons why in the Vichy result there's an external body force. And then there are few generalizations of these ideas in the stochastic framework. Here I'm just mentioning two papers in this direction. Okay, so this is essentially the first evidence of non-uniqueness and ill-posedness in this problem. The second one is based on this work of Bressan and Chen, where they propose a similar no-uniqueness scenario, which is supported by numerical simulations. And it has, I mean, a few features in common with the no-uniqueness result of Vichy. But to date, there's no rigorous proof of this result. So it is not known whether uniqueness, as explained in this paper, can really happen. But let me just quickly explain the main idea. Again, we consider the two-dimensional space. Now the external body force is equal to 0. So we just added the two-dimensional Euler with certain initial condition. And the claim is that there exists an initial condition with this form. Here I'm using just polar coordinates. So it has a power law singularity at the origin and some angular profile phi theta. And then the expectation is that, so this is just a picture of the initial condition. Then we would like to regularize this initial condition, which is singular just at the origin, r equal to 0, in two different ways. So we cut a small ball around the origin, say of size epsilon, and we replace the ball with 0 in this second picture and epsilon to the -1 over alpha in this first picture. So in both cases, we get a bounded initial condition. And it's not smooth, but it's bounded. And in particular, there exists a unique solution oops. Okay. So in particular, there exists, we know that by Yudovich theorem, there exists a unique solution starting from this initial condition and this initial condition. And the claim is that the two solutions behave in a very different way. They are both self-similar, but one is just rotating around the origin, while the second one is rotating around two distinct points. So after regularization, we expect, Bressan and Chen expect to find, to get two completely different behaviors. And this for every possible regularization parameter epsilon positive. Okay, this is a super nice no uniqueness scenario, and again here there's some sort of symmetry breaking. There's some form of instability in self-similar coordinates, but to date there's no rigorous proof of this phenomenon happening. Okay. Okay, and yeah. Oh. There's some, okay. Now, I want to talk about flexibility in Euler equations and then connections with convex integration, and talk about a convex integration construction showing flexibility in the two-dimensional problem, even when p is bigger than 1. This is the main point of this last part. What do I mean by flexibility? Well, here is a kind of results I have in mind. This is this statement here is due to Scheffer back in 1993, and Schnirelmann has simplified and improved a bit this result in 1997. And this was essentially the first example of say, wild solution to the two-dimensional, wild distributional solution to the two-dimensional Euler equation. So Schaeffer managed to construct a non-trivial solution in this class, L2 in space-time, with the property that it is compact in space and time, which is pretty wild, given that smooth solutions to the two-dimensional Euler equation are expected to conserve the kinetic energy, so the L2 norm in space should be constant in time. Then, in two papers, Camillo and Laszlo introduced a general framework to construct solutions with this kind of wild behaviors. And here is a statement from their paper in 2013. And it says the following: essentially, it is possible to prescribe the kinetic energy profile of continuous solutions to the Euler equation. So as I said, in the smooth class, one expects the kinetic energy to be constant in time. But in the class of continuous solutions in space and time, one can use this construction to essentially prescribe the kinetic energy. Given any continuous energy profile, any function E of time, there exists a solution to that. This is a statement about the three-dimensional Euler equation, but still one can find a solution to the three-dimensional Euler equations with this given energy profile. And maybe the most famous application of this kind of construction is the solution of the Onsager conjecture, which is nowadays is a theorem. And it says that if solutions to the three-dimensional Euler equation are Holder regular with exponent bigger than a certain threshold, 1/3, then they have to conserve the energy. And this has been proven by Konstantin ETT back in 1994. The second part, the flexibility part, has been proven using convex integration by essentially improving upon this result and by constructing weak solutions to the Euler equation in the Holder class, C alpha with alpha strictly smaller than 1/3. And this has been done by Isset in 2018, and I'm also mentioning the follow-up paper by Buckmaster, Delellis, Zwickriedi, and Wickel. And actually, this convex integration approach turns out to be very flexible, and it can be applied to different nonlinear models. One very important example is the construction, the first example actually, of flexible solutions, flexible weak solutions to the Navier-Stokes equations. It has been obtained by Buckmaster and Wickel in 2018. It is possible to apply these ideas to active scalars, SQG equation in particular, and it is even possible to get interesting results on linear problems, like linear incompressible transport equations within the framework of the Lippern-Alliance theory. So this will be actually relevant in a second for this talk. Okay, let me just quickly explain what's the key point behind convex integration constructions and why it's somehow very hard to get flexibility out of this methodology in the two-dimensional setting when the vorticity belongs to some LP space. Now, the idea is the following. So we essentially relax the problem. So instead of Euler, we study this system, which is nothing but Euler with a reminder here, with an error term, and we encode the error in a tensor, the Reynolds the Reynolds stress tensor, and we write it as a divergence of this tensor. So typically one gets solutions to this or sub-solutions to the Euler equation when filtering turbulent solutions. So if you pick a solution to the Euler equation and you cut high frequencies or you apply a convolution, whatever, because of the nonlinearity, the regularized vector field and pressure is not going to solve the Euler equation, but is going to solve the Euler-Reynolds system with a Reynolds stress tensor depending on the commutator between the quadratic interaction and the convolution or whatever regularizing operator we apply. Convex integration goes a bit in the opposite direction. So instead of regularizing turbulent solutions, we start from a subsolution. Maybe sometimes we have to assume certain properties of the subsolutions. In other applications, subsolutions are just functions, random function. We don't have to specify exactly what are the properties of the subsolutions. But then we try to reduce the error by means of an iteration scheme, eventually converging to a solution to the Euler equation with zero error. This is the idea. So instead of eliminating high frequencies, we add back high frequencies to converge to a solution to the Euler equation. And here is the general strategy. So we start from a subsolution, and then we try to define a sequence of smooth solutions to the Euler-Reynolds system. And we hope in the end to show that the error term RQ is converging to zero in some topology. This is just a possible choice. And of course, along the iteration, we would like to control a bit the regularity of the solution, and the minimal requirement is to at least control the kinetic energy of the velocity field. But in order to say something interesting in the regarding the uniqueness of solutions with vorticity in LP, one has to control also the vorticity of UQ in some LP space. So this is what we need to control. Now, here is how we perturb solutions at the qth step of the iteration in order to get the qth plus 1 approximation of the Euler equation. So we add a term with this structure. Here, lambda q just denotes the typical frequency at the qth step of the iteration. And this is an increasing sequence, and it's like increasing quicker than exponential. And this object here, this lambda q plus 1, is the main, is the so-called building block of the construction, and it has exactly frequency, or more or less frequency, lambda q plus 1. And the profile W has to satisfy certain properties, and an important one is that W is an almost solution to the Euler equation, an almost steady state to the Euler equation. This is important for the quadratic cancellation step. And this term here is the slow variable. You should just think of it as a constant function. Is not constant as it depends on the error at the previous step. But the frequency of the error at the previous step is lambda q, which is much smaller than lambda q plus 1. So from the point of view of the fast variable, this is just a constant addition to the, it's just a constant in front of the building block. Now, what's the key point is the quadratic cancellation as a consequence of the interaction between the perturbation in the quadratic nonlinearity of the equation. So when you plug these ansatz into the equation, you get many terms. The most important one is the nonlinear term divergence of the perturbation tensor itself. So this is the only nonlinear interaction between the high frequency term and itself. Now, the idea is that out of this interaction between these two high frequency waves, we get low frequency terms, and we design the slow variable in order to match up to a very small error, the error at the previous scale. So to do something like, and of course, then we have high frequency terms left over. And the idea is to eliminate them by inverting the divergence. And here is where I have to impose assumptions on the profile W. But I mean, in order to produce a low frequency term which matches exactly the error at the previous scale, what I need is to assume that the average of the nonlinear term tensor product itself is more or less 1. So this amounts to a normalization in the L2 norm. I'm asking that this W has L2 norm equal to 1, essentially. And I need this low coefficient here to have magnitudes more or less the square root of the error, as the square is what appears here, and the square has to match exactly with the error. Okay, so just to have a picture in mind, so the perturbation like this. So it is lambda q plus 1 periodic. So this is 1 over lambda q plus 1. And in this, I mean, in the version of the convex integration I'm applying in the two-dimensional setting, I also have a second length scale, which is much smaller than 1 over lambda q plus 1, is 1 over mu q plus 1. So this is much smaller than this. So the perturbation looks like this. So it is very, very concentrated at scale 1 over mu q plus 1, which is way bigger than 1 over lambda q plus 1, and then lambda q plus 1 periodic. And this is what I denoted W, lambda q plus 1, and what we plug in is this times some slow variable. Okay, great. Now let's see what we can say. Okay, now we tried to apply this construction with Maria back in 2021 to the problem of uniqueness in 2 dimensions with vorticity in LP. And what we get was the following not very satisfactory result. So we could construct convex integration solutions of the 2-dimensional Euler equation, L2 in space, with bounded kinetic energy, with a compact support in space and time. So some flexibility here is going on, and vorticity in the weak L1 class. So not even L1, just L1 infinity. And this actually means that, I mean, this is not even it's not even the space here is not even a space of distribution. So it's a bit very bad space where to have a derivative. We understand this inclusion as follows. So we have this approximation, smooth approximation coming from the iteration in the convex integration scheme, and we can control the L2 norm in space uniformly with respect to time. We can control the error; it goes to 0. and we can control the vorticity, but just in L1 weak, not in L1. We get some limit in L1 weak, but it's not even clear what's the meaning of this limit omega. And Bach and Modena improved a bit this result by showing that actually one can converge, one can control Hardy norms, but again, there's the constraint S smaller than 1. So it seems that one cannot even get an integrable vorticity using this technique. And actually, there's a very clear obstruction coming from the quadratic cancellation of the error. And here is the obstruction. So this is the ansatz, this is the perturbation. And as I said, in order to get low frequency terms, we need to normalize the building block W in L2, and we need to normalize it to have norm exactly equal to 1. But on the other hand, if we check the magnitude of the differential of UQ plus 1, or more importantly, if we check the differential, the sides of the differential of the perturbation, so it turns out that the differential of the building block is lambda q plus 1, the frequency, times the L1 norm. I mean, I'm checking the sides in L1, times the L1 norm of the profile. But by Sobolev embedding, the L1 norm of the profile is always bigger than or equal to the L2 norm of the profile. So all in all, one has this very bad lower bound on the L1 norm of the perturbation. The differential in L1 is bigger than the frequency parameter. It's bigger than lambda q plus 1, and lambda q plus 1 is like growing more than exponential, faster than exponential. So it seems that there's no way to get convex integration solutions with integrable vorticity, at least if one sticks to the quadratic cancellation trick. And more recently, we managed actually to go beyond P equal 1 and to construct the first example of very flexible solutions to the two-dimensional Euler equation with vorticity in LP, P positive. I mean, I have to say, P is not so big, it's slightly bigger than 1, but still bigger than 1. And those are the two statements we have. One is flexibility and one is just non-uniqueness. The first statement says that we can essentially, up to a small error, we can prescribe the starting velocity and the velocity at time 1. So given two reasonable velocity fields, we can construct, and some parameter epsilon, we can construct a solution to the two-dimensional Euler equation with vorticity in LP, which is epsilon at time 0 is epsilon close to the starting velocity field, and at time 1 is epsilon close to the ending velocity field. So in particular, one can construct non-conservative solutions. Entropy is not conserved. And this is just about no uniqueness. There exists a very big set of initial velocity fields, again, in two dimensions, such that we have infinitely many solutions of the two-dimensional Euler equation with vorticity in LP starting from those initial conditions. So uniqueness.
The same condition in P?
The same P, which is more or less of this size. Okay, let's see. Let's make a few remarks about the structure of the solutions. So clearly, given this flexibility statement, those solutions are not, the kinetic energy is not conserved. LP norms of the vorticity are not conserved as well. We expect to modify the strategy in order to make them dissipative, but this requires a bit of technical work, so we don't know yet if it is really possible, but it seems reasonable. And here is a comment about energy conservation. It's known that when given a solution, again, in the LP with vorticity in LP, when P is bigger or equal than 3/2, then the kinetic energy is conserved. Our P is way smaller than this. And a natural question is whether one can construct non-conservative solutions for every P smaller than 3/2. And yeah, I mean, we can prove this only for a very limited range of exponents around 1. But in principle, it might be possible that energy non-conservation holds up to 3/2. That's an open question, I don't know. And regarding the vorticity formulation, when P is so small, close to 1, the vorticity formulation is distributionally doesn't make sense because the velocity field times the vorticity is not an L1 function. The first exponent where it makes immediately sense is P bigger than 4/2. And again, our exponent is smaller than this. But actually, we can check that our solutions satisfy the symmetrized weak vorticity formulation. So they are solution to the Euler equation in velocity form, and they satisfy in this weak formulation also the vorticity formulation of the two-dimensional Euler equation. And finally, our solutions are not vanishing viscosity solutions. And this is because by a theorem of Cheskidov, Filio, Lopez, and Schwitkoi, vanishing viscosity solutions with LP vorticity, they do conserve the energy. So our solutions they don't conserve the energy. So in particular, they are not vanishing viscosity solution. So yeah, they are pretty rough and maybe not so physical. Okay, what are the new ideas to get beyond the threshold P equal 1? So the main idea, the main idea comes actually from our previous paper about the transport equation in the Di-Perna-Lyons framework, where we realized that a certain very strong form of spatial inhomogeneity is necessary in order to get sharp non-uniqueness results. And in order to apply this principle in the convex integration framework, what we did concretely is to eliminate spatial periodicity from the perturbation in the convex integration scheme. So in other words, this is no longer the picture of the perturbation. The new picture is simply not periodic. It looks like this. And we are leveraging the time dependence in order to reconstruct some interesting high frequency structure after time averaging. I'll show a few pictures in a second. And another important technical point is that we need very precise almost solutions to the Euler equation in order to make this work. And here we use the Chaplygin-Lamp dipole, that they are exact solutions to the two-dimensional Euler equation in R2, and we use an approximation to make them periodic in space. But let me check the time. Do I have like 10 minutes? Yes. Okay, great. I would like just I would like to explain a bit this first point about spatial inhomogeneity and connections with the transport problem. So here is the toy model I want to consider. This is just the passive transport equation. U is a velocity field, is given, and it belongs to a Sobolev class, W1P. Rho is the vorticity, so we fix the initial condition and we look for solutions in Li. This is the Di-Perna-Lyons framework. In 1989, Di-Perna-Lyons proved that this problem is well posed as soon as 1 over p plus 1 over r is smaller than or equal to 1. So again, here the domain is the torus of any dimension, say dimension d. Then this is a convex integration result. By using convex integration, it is possible to show that in this range, when 1 over p plus 1 over r is bigger than 1 plus 1 over d, and d again is the dimension of the domain, in this range, one can construct convex integration solutions. In particular, the problem is very flexible. One can show no uniqueness, a series of wild behaviors for the linear problem. And notice that there's a gap between the well-posedness range found by Di-Perna-Lyons and the ill-posedness range obtained by convex integration. And in 2020, in collaboration with Camillo and Maria, we discovered a third range of exponents. If we restrict to the class of non-negative densities, so if we assume that rho is non-negative, this is, it's not so restrictive. I don't want to focus on this assumption. But under this extra assumption, it turns out that the problem, the transport equation, is well posed in this range. And it falls exactly in between the Di-Perna-Lyons range and the convex integration range. And only recently, we realized that the third one was the sharp range. And we managed, together with Maria and Anush, we managed to construct no unique solutions to the transport equation in this range, which is exactly the complement of this. And what we constructed is something like this. So at time 0, we have the constant density. And then we find a solution to the transport equation with velocity field in W1P. The density belongs to LR. And at time 1, we get this configuration, where the white part is where the density is 0, and the red part is where the density is constant. Some number slightly bigger than 1. So if this is 1, this is slightly bigger than 1, but still. And the solution is non-negative. Now, let me just describe a picture of what is happening here and what are the, say, connections with convex integration results. So this is the evolution. So instead of building a dynamics from here to here, let's do the opposite. We can, of course, reverse time in this problem. So let's start from the 4 squares configuration and try to converge at time 1 to the constant density. And here is what happens in our example. We start from this 4 squares, and then after some times, I don't want to be precise on the time length, but after some times, the first square over here is broken into 4 pieces. Then we move. This is just a rigid movement of each of the small cubes. We reach this configuration, and then we restart by breaking only this small cube again into 4, and then we make the 4 small cubes, equispaced again. And notice, so first of all, notice that here there's some sort of self-similar behavior. Going from here to here is nothing but applying the whole dynamics rescaled only on this big square over here. So it has some self-similar feature, but
You are still talking about the linear flow?
this is the linear flow. This is the linear flow, yeah. And then how we continue? Well, anytime we pick this bottom left cube here, we break it into 4, and we keep going like this. At some point, we get a density, a constant density over here, and then we move on and we start breaking this other cube. We keep going, and at some point we get the constant density over here, and so we restart from here.
But if you keep making your boxes smaller and smaller, why do you actually get the constant density on a box of a fixed size?
They weakly converge to the constant density. I'm making them smaller, but I mean, it's literally, it's just weak convergence. It's just weak convergence of this density to the.
But it seems your region is becoming negligible as you actually go down the scales, no? What am I missing? Because I mean, you divide by 4 the first time, by 16 the second, by 64 the second time. So what I'm not understanding is why, because you only do it on a third of the.
On 1/4, yeah. I just break the smallest one in time.
And so the others are untouched.
The others are untouched.
But then it seems you're touching.
But I mean, here you have infinitely many time scales that are nested. Maybe, I'll try to.
Okay, then I'm not understanding.
But I mean, let's consider the following easier way to do the construction. The natural and much easier way is to break all the 4 cubes.
Yeah. Yes. Then I would understand that you're doing.
And repeat anytime you break 4, and you go on like this. And this makes perfect sense, right? Because I mean, you get here you get from 4, 16, 64, and so on and so forth. Great.
And it's because you have full freedom of U, basically. You arrange your U to make it.
I have full freedom on U, yes.
That's how it works. It's because it's passive.
Exactly. Yeah. That's true. Yeah. Now, but let's consider the easy case. In the easy case, what happens is that you do converge here, right? Mm-hmm. But if you check the integrability, you get the convex integration parameters.
Mm-hmm.
You get convex integration range.
Okay.
If you instead break cubes in this asynchronous way, you get up to the sharp range.
But when do you start breaking, like, the other? Because at a certain point you have to break also the others, no? I mean,
yeah, you have to, but I mean, you have infinitely many. I don't think I'd be capable to explain this in words.
Yeah. Okay.
Here I'm trying to separate the time intervals just to draw a good picture, but this is happening like it's more simultaneous than what it looks in this picture.
But what happens with the area at each step? I also don't see.
So what happens with the area?
Basically the same question.
The LR norm, it's always under the L1 norm is the balance.
I think he's doing the same objection that I'm doing. I look at your pictures and you're acting on a smaller and smaller area each time. So the area of the things on which you're acting is actually going to 0. That's why I don't understand why, on F,
the fact is not really like, those are just separate snapshots, but it's not really like this. You're not just acting on a small region every time.
Okay.
You're not really doing this.
Okay.
There exists a sequence of times when you see something close to this, but you're not really just acting on a small cube every time, like in this picture.
Okay.
Essentially, you're saying that separating scales is more efficient for integrability.
It's way more efficient for integrability, exactly.
Right, but this fact that you're doing it uncountably many times, if I want to identify any possible point or region in space, and you're going down, countably many scales, you actually have countably many choices of where to put your stuff, and it looks like the sequence of zeros and ones, which is not countable, it's actually uncountable. So that's what kind of.
Okay.
That's what,
I'm not sure I'm understanding your concern.
That's what kind of puzzles me. But okay, maybe.
I mean, I can guarantee you can.
I can ask maybe later.
I can
how it
explain
really
the
works.
steps
Yeah.
more in details. Yeah, so what's the message here? I mean, it's not important to understand all the specifics of this construction. It's just linear. But the message is that you try to somehow intervene and modify your solution at the given time on a smaller possible region. And this is not what happens in standard convex integration when you add a perturbation which is periodic with some very huge frequency parameter lambda q plus one. So in particular, the perturbation looks like very homogeneous, at least at scales bigger than 1 over lambda q plus 1. It is not if you go down in scale and you have this very concentrated regions, but at scale bigger than lambda q plus 1, this looks super homogeneous. And the attempt to implement this kind of asynchronous move and inhomogeneity in the construction leads us to this idea. So we get rid completely of the periodic structure, and we consider perturbations that are essentially jets moving along a certain trajectory. And now the frequency parameter in this scheme is given by this scale over here. So the distance between I mean, yeah, it's related to the periodicity of this trajectory wrapping around the torus. And the idea is that time by time you see something happen only on a very small specific region of the space. But if you average in time, you get a configuration like this, which looks more periodic. And this is what is used to perform the quadratic cancellation of the error. And there are few technical points. So you have to change the size of the jet. You have to allow for variable velocity, and you have to completely get rid of the slow variable over here, as you no longer have a fast variable. So in particular, it doesn't make sense to add the slow variable. And once you get rid of the slow variable, you have to find a way to reconstruct the error based on the variable speed of the jet. And given that those are almost solutions to the Euler equation, if you change the speed, you have to change the size. And again, this is a bit technical. In order to make this work, you need a very precise almost solution to the Euler equation with compact support. And this is what we used. The core of the Lamb-Chaplygin vortex, which is a dipole, which is a solution to the two-dimensional Euler equation. A true solution to the two-dimensional Euler equation, at least in R2. Okay, yeah, I think I can stop here.
Questions? May I ask a naive physicist question? You are describing this non-uniqueness and all kinds of ways to approach it. Is there a method to supply some extra boundary conditions which would make solutions unique? Like, for example, if you consider a limit like we did, remember, of Navier-Stokes with this close to zero, you might try to derive boundary conditions at singularities like vortex sheaths and vortex lines or some other singularities. So that philosophy, does it apply here? Could you find some boundary conditions for pure Euler system which would reflect the limit of the Navier-Stokes in this quantity?
So to begin with, I don't even know how to construct wild solutions or how to construct flexible solutions as vanishing viscosity limits. this is already, I mean, this is already an extra restriction.
I think what he's suggesting is some type of entropy condition, like, you would take on, like, a compressible Euler, for instance.
Yeah, like
if you have
in the whole domain, it's Euler, and very in a small vicinity of singular region, it is Navier-Stokes. That's what I mean.
like, think about, kind of non-physical shock and physical shock.
I
We don't know.
I don't have any idea of what to do.
So we don't know of something that works. Unfortunately, we only know of what doesn't work. For instance, a kind of, a condition like it's used on compressible fluid dynamics of like just saying the shock is non-physical, it's not working in this situation. So can I nag you again about, these boxes? So, but let's say, only, do I understand correctly that the only thing that you want to do is you want to act on each box one at a time? So, I mean, like, say on picture 3,
Yeah,
instead of doing what you do on the
picture
smallest
3,
ones, can I actually break the big ones?
picture 3 is this one, right?
Yeah, so picture 3, I mean, before I actually get to D, can I actually break the big ones? As long as I don't act on the other ones.
I mean, you want to break this.
Yes.
I mean, you can, but you get the wrong range of exponents.
But not all together. Just, separately as you did at the beginning. I mean, you just sit
No,
down.
it doesn't. I got it. No, it doesn't work. You have to first finish to destroy this.
But I mean, how do you finish to destroy exactly the thing as you're getting smaller and smaller at each scale? So, like,
I mean,
why all of a sudden you draw me a picture which is like, in
like this.
Yes, I mean that thing is infinitesimal though, right? I mean, it got to 0 in your construction if you keep refining.
I mean, this comes out of a fixed point argument, and I cannot really envision well.
I mean, because it somehow you acted on 4, then on 1/16 of your region, on 1/64, and then all of a sudden, actually, I get
Let me see if I can find a reasonable explanation in words. Yeah, I mean, I don't know how to describe it.
Because you see, my point is just that a finite time, a finite time sort of finished, right? And why didn't you simply end up on the bottom left corner, just that point in the end? Right? I mean, because if you keep making a smaller and smaller square, no? I mean, why actually didn't I get just?
The actual construction is much more simultaneous than, is much more synchronous than this.
Okay.
And
So
there are nested, countably many intervals of time nested into, I mean.
Okay, but you're doing something at a synchronous time. You're not doing it really there.
I mean, I'm not really just breaking only one specific thing at each interval of time.
Yes.
That's for sure, no.
That's what I
don't have a better way to picture things if I don't make this kind of strong approximation.
There's a moment in which you're acting on more spaces.
Yes.
Okay.
But I'll try to explain the construction, how it really
works. Okay, and I mean, now I understand that it is possible. Okay.
Yep.
You didn't quite explain how the convex integration fits into this picture. You did
from this, you mean this picture? No, I mean, from this picture, we simply, we were working in these 2 different problems, one linear and one nonlinear, and we realized that this trick of trying to make things very asynchronous works in the linear setting. And then the question was, and here, it was meaningful because we had essentially the same, this construction is essentially helping us going beyond the critical range for convex integration, coming from the very same abstraction we got in the 2-dimensional Euler problem. So
the mechanism of convex integration is the same as
the mechanism of convex integration in the linear and the nonlinear problem is the same, and the suboptimal range here is it comes from the very same constraint. I explained for the Euler equation. So this is essentially the same as saying that the vorticity cannot be integrable because of by applying a convex integration. It's the very same. Is the very same constraint. And
Where
here,
is the number? Where did your number come from? This 1 + 1?
you mean this or this?
Well, yes, the general one.
I mean, this is just is related to the Sobolev scaling. Is the very same constraint here. So here the constraint is because of the normalization of the L2 norm. The L2 norm is equal to 1, and then Sobolev embedding.
No, but you're just able to go a little bit beyond 1, right? 1 + 1,000 or something like that.
Yes. The question is how I get beyond.
Yeah.
The new approach. Okay, the new approach with no periodicity as a different scale. Now 1 is again a threshold, but you can reach 1. To go beyond, you have to leverage the smallness of the slow variable. I'm cheating a bit because there's no slow variable here, but there's a quantity which resembles the slow variable in this framework. And once you can make this building block W11 with differential with L1 norm of the gradient of sites 1, then to get slightly beyond the p = 1, you just try to leverage the smallness of this coefficient in front. So from the point of view of the scaling, what happens is that we go from L1 norm big to L1 norm equal to 1 with this trick. It's a very tiny gain, but then leveraging this, you go slightly beyond. While in the linear setting, you beat the range by a certain amount. But this is something that we don't know how to reproduce in convex integration. Yeah.
So can you go back, please, to the slide where with the Sobolev embedding?
Yeah.
So here.
Here.
Yeah. So here you don't really take into account the RQ to the 1/2, right?
And you mean the slow coefficient?
Sorry?
You mean the slow coefficient?
Exactly. In the Sobolev inequality estimate that you write, you don't have you essentially estimate A by 1, right?
Yeah. Yeah.
Which is not really true in any, unless you converge in L infinity, right?
You're right. But what you can gain from this coefficient is more or less the square root of the error at the previous scale. It's never enough to beat lambda q + 1. There's no way, I mean, yeah, that's an approximation. I'm simply saying the problem comes from the fact that this is of size lambda q + 1. In reality, the size of this is lambda q + 1 times the small coefficient. But again, the small coefficient, yes, is small, but is never small enough to let you control the lambda q + 1. So you're right, I should consider this, but again, it's not really helping here. This is helping when if you can get something of size 1, then you can use the slow coefficient to kind of make it converge and gain some epsilon. But you never beat a full frequency parameter lambda q + 1 appearing in this calculation.
Okay, maybe we thank Elia again and